Perfect. So there's our email address if you'd like to get a hold of us. We'll start with just some brief introductions. My co-presenter is Lexi Langellier. She's currently a senior at Trinity Christian College, which is a four-year college just down the street from me at Moraine Valley. Next fall, she's going to be attending a yet-to-be-chosen school pursuing a PhD in applied mathematics. Her interests include data science and graph theory and cryptography. Just on like a personal thing, she's just gotten some acceptance for grad schools already starting to roll in. So claps in the chat for Lexi. Congratulations.
So this is Peter Keefe. He's been teaching math at Moraine Valley Community College since 2013. He teaches mostly calculus, but he's also interested in statistics and data science at the community college level. He wants to add more coding and simulation type activities into the undergraduate math curriculum.
So let's talk a little bit about how we got this thing rolling. Anecdotally, for a long time, I have noticed that students struggle with understanding limits in first semester calculus. It's a topic that they continually kind of run up against. And I've begun thinking that I'm pretty sure that students are approaching the limit topics and problems a little bit differently than the way that they approach things with derivatives and integrals, the other two big topics in calculus. So for these three pillars that we have, I really think that students are just thinking about these things and approaching them very differently. And we wanted to get some insights on how students are thinking about these three big topics to try and figure out how we might understand their misconceptions and try and build up good intuition, connect those topics with themes to really keep creating a good calculus course that's going to kind of set them on the right trajectory.
I originally joined this project to fulfill my field education requirement for my degree, but with my interest in data science and my future goal of wanting to become a professor one day, I learned a lot from this research and overall experience.
So probably the first thing that we should do is start off with just looking at what's been published on how students are thinking about these kinds of topics. So here's the first paper that we have. I'll put that link in the chat if you're not following along on the slides. This is Models of Limit held by college calculus students. It's a 1991 paper by Stephen Williams, and I think it's probably a pretty kind of foundational paper. In this, students were presented with a bunch of questions and they were interviewed about those questions. That kind of structure is really common in this type of research. If we're trying to figure out how students are thinking about this, it makes sense to set up some long interviews to kind of dig into how they're thinking about these. The questions that were given to students were intentionally built to try and have them think about limits in different ways, to kind of bounce around between these different models that they might hold in their head about limits. And then they were talking through the problems with the interviewer, and they weren't just talking about what the problems themselves were, but the interviewer was really focusing on trying to have the students explain all of the ideas and conceptualizations that they have. In some cases, it was asking students to, literally draw out some of the models that they're using and really trying to kind of play that part out. The big findings from here is that kind of no matter what, most of these students ended up going back to this. I love this sentence that they have, a procedural dynamic view of limit. That's an idealization of evaluating the function at points successively closer to the point of interest. This sounds like probably the way that most of us that teach calculus introduce limits. But the interviewers found that it was difficult to have students move past that model. And because of that, it was really hard to get to a more formal or precise definition of limits, whether it's, the epsilon delta kind of analysis centric definition, or maybe something a little bit more topological with open sets. It was hard to have students motivated to need that kind of thinking. Part of this, the paper claims, is due to the students' background and experience and the way that they're thinking about mathematics. Calculus 1 course probably doesn't have a lot of math majors compared to maybe engineering majors and things like that. And so maybe these students are thinking about math more from a utilitarian How can I use this to solve a problem, as opposed to, valuing kind of the abstraction side of things. So because of that, they found it was really difficult to motivate students to move past this procedural dynamic view of limits. And that's something that we're going to see as kind of a theme in these kinds of research studies.
So the next limit research we looked at was from 2013, examining the discourse on the limit concept in a beginning level calculus classroom. So the way they took data for this study, they videotaped classes and took observations about how limits were being taught. There was a diagnostic survey at the end of each lesson, which was used to select students for interviews later on. There were 4 audio-taped task-based interviews with 6 questions, 2 directly from research exploring student learning of limits, and 4 designed by researchers with student difficulties and instructor discourse taken into account, and they also used the students' written work. So to classify this data, they used 4 different techniques. So for word use, they were looking for colloquial or like everyday sense, like what is speed, operational, so dynamic motion, the function value gets closer to 5 as x values approach 1. Objectified, so distinct math entity, like the limit is 5, the limit does not exist. They also looked at visual mediators, so written words versus graphs or symbolic representation. And then the routines in the classroom, so whereas word use being used more, visual mediators, narratives, algebra-based routines, most used by the instructor, and then when and how were these routines used. And then less focused on in this research was narrative, so definitions, theorems, or facts. The analysis was that the professor used mostly objectified language for word use, but the students, they learned mostly from the operational. That's what they hung on to most. And they actually counted how many times word, like the type of word use happened. So the professor used objectified word usage 634 times versus the operational, which is only 139 times, which is interesting that that's what the students kind of hung on to. And then for the visual mediators, the professor mostly used symbolic representation, but the students hung on to the graphs more, and that's kind of how they explain things. And then for the routines, we were looking at, are they looking at the limit as a number or a process? So when the professor was teaching, they referred to it as a number, but the students referred to it as a process when they were explaining it. So from this research, it's really interesting that how the instructor was teaching the material is not what the students retained most.
The next one that we looked at is the mathematical beliefs and conceptual understanding of limit as a function. This is a 2000 paper. It was published in the year 2000. There's a link in the chat for that. And for this one, they sorted students into quadrants. So we have an axis that represents the content beliefs that the students hold, and then another axis that represents the sources of conviction. These titles, I think, sound so dramatic to me, and I love that. They were thinking about conceptions about the real numbers and infinity and what functions are. So notice these things that they're classifying are not directly about limits, but these are really foundational topics to how we think about limits, right? We need to know how the real numbers work. We need to know some of the nature of infinity or be able to explore some of that. We need to know, what models of a function we should be holding. And so they took those kinds of conceptions, those content beliefs for students, and tried to put them on a spectrum there about what kinds of things they believed about, the density of the real numbers to some degree, or again, the nature of infinity. And they found that the different understandings there obviously leads to different levels and kind of understanding of limits and how we can use those and the different models of how we might understand those things. And similarly, if you think about the sources of conviction, this seemed to be mostly about what students believed about the nature of mathematics in general. So why we think these things in math are true. It seemed to, from the researchers' viewpoint, kind of range from a low-level view of math being a collection of facts that we memorize, up to kind of a more higher level view of some sort of a organized structure, being built out of axioms that we might agree with a little bit more. But they sorted students onto this spectrum as well, and then tried to see how that impacted how students viewed and understood limits. And you can imagine that both of these axes definitely have a big impact on this. One of the things that I thought was interesting is that the content beliefs themselves, the real numbers, the nature of infinity, what functions are. These are topics that are largely happening before students enter into a Calc 1 course. And those were kind of picked as some of the big topics that really impact how students are believing or understanding limits.
So the one we looked at for derivatives was from 2017, an exploratory study on student understandings of derivatives in real-world non-kinematics context. So there was two ways they collected the data. The first was qualitative interviews, which was a more open and inductive analytic technique. And then they also used quantitative surveys, which was more pre-structured or deductive. They were looking at how students classified different models for derivatives outside of basic kinematic examples. So how do students treat other symbols in their expressions? How do students interpret rates of change? And how do students invoke time even when it's not required? So from this research, they noticed that students were able to switch between mental models of a derivative to match a problem, even in examples where it wasn't always the appropriate model. Like introducing time. So there was an example when students were looking at radius. They looked at it as if the radius was increasing at a steady rate in time to help explain that the volume would always grow, but by a smaller rate at first and then by a larger rate later. So they were invoking time, and it seemed to be more than a way of understanding for particular derivatives only in helpful instances. This was in contrast with limits, where students seem to continually converge on the same point-based model, no matter the circumstances.
And then our last one that we looked at is, or that we're at least going to share with you, is the constructing the integral concept on the basis of the idea of accumulation. Like in the title, it says this is a suggestion for a high school curriculum. This is a paper from 2013 where the authors are in Israel. And so they were looking at kind of a standard high school calculus curriculum there, which from what I could see really matches pretty clearly with what students might see in a first AP Calc course or in a first semester college course. There didn't seem to be many differences. They also were looking at some other kind of international high school calculus courses, and it seemed to be pretty much the same thing. Their big conclusions I didn't think were jaw-dropping or anything like that, but I wanted to reference here because they really resonate with my experience and probably others here who have taught calculus before. The standard way of introducing indefinite integrals as antiderivative families, or this operation that undoes a derivative, and then definite integrals later as area under a curve, it's useful in that it gives students technical skills to solve all the types of problems that we want to ask, right? So students can anti-differentiate at the end of Calc 1, they can construct a Riemann sum, and they can evaluate a definite integral. But what they noticed in this paper is that the idea of accumulation in general was really easily lost in this kind of structure. There wasn't that nice theme tying things together. They had a whole bunch of suggestions in this paper on how to weave the ideas of accumulation in before we get to the fundamental theorem of calculus. The fundamental theorem of calculus is the wonderful thing that links indefinite and definite integrals together, right? It connects limits, derivatives, antiderivatives, and area all together. But they noted that including that so late in the curriculum might not always be as helpful as we think it is. If we want to build up that theme earlier, we need to start addressing it a little bit earlier so that it's presented early and clearly to students, because having that connection in their minds is going to be more helpful while they're learning this. That's something that we've probably all noticed. That that big idea is hugely important and helpful, but having it come late in the curriculum may not always be ideal. So that's just a snapshot of some of the papers that we were looking at to try and give you a feel for what we've noticed and what the kinds of things we're thinking about are. So what is the actual study that we did? What was the project that we were working on? So this is our approach. We started off with 3 optional surveys for Calc 1 students throughout the semester. So this is while they're enrolled in a Calculus 1 course, while they're learning about all these things. We had a survey on limits, a survey on derivatives, and a survey on integrals. And each of these surveys were given a couple of weeks after we, wrapped up whatever unit that we were talking about. So by the point that students are seeing these surveys, the content is relatively fresh, but they've had several weeks to kind of build on that and master it and think about it and be assessed on it. The only exception is the integration one. That one came right at the end of the semester during like a review week. They were finished learning about integration for the semester, but didn't have as much time to kind of sit with it. So that's something to think about. I don't think that's a big limitation for us though. The survey was split into 2 different parts. So the first part of it, we just asked students to write some written responses to describe limits, derivatives, and integrals in general. We had some prompts for them that they could answer, describing the main ideas of them, talking about what was important in these kind of objects that we're studying for the semester. And then the second problem, or the second part, was that we gave students a bunch of limit, derivative, and integral problems and had them group them together. So on the limit survey, it was, here's a bunch of limit problems, split them into groups based on how these problems are similar to each other. We tried to not give them any, leading hints on what we were thinking similar meant. So they got to create their own criteria for what that meant. And that was what we were really interested in, right? Do students think about limit problems as similar or different to each other in a different way that they do derivatives or integrals? The analysis that we did, we took kind of a network analysis approach for the grouping part of things. And so we looked at essentially how often students grouped certain problems together and then tried to run, some kind of algorithmic stuff on there to see if we could find some of the natural or common groupings that we had, to see if there was any kind of structure to how a whole class collective grouped these problems together. And then for the written out responses, we're going to apply a kind of sentiment analysis approach. Sentiment analysis is commonly used in, the like analyzing written out stuff. It's used a lot in reviews or in like tweets or something like that, where what we do is we assign kind of a positive or a negative score to sentences or paragraphs based on a kind of positive or negative sentiment. So if something is really positive and optimistic and uplifting or whatever, we'll have a high positive score. And if it's, negative, gloomy, angry, sad tone, it'll have a negative score. And this is obviously useful for kind of processing language in a bunch of instances. We didn't really care too much about positive or negative sentiment. So what we're doing right now is trying to align those things on a different spectrum, where instead of positive or negative sentiment, we're thinking about kind of a conceptual understanding versus a computational approach, to simplify things. That's kind of the spectrum that we're looking at. Why are we doing it this way? First off, there was a big limitation on the scale of the project that we could do. We don't have funding to be able to introduce this out to other colleges and other first-year calculus courses. So we just kept it kind of in-house. But also that was kind of fine, because the population that I'm concerned with is the groups of students that are taking the Calc 1 courses that I'm teaching. So I was happy to keep this localized to, my specific courses and the students enrolled there. And then the network analysis, we thought would be an interesting technique to use. I have some background in, cluster analysis and data science and other kind of statistical type clustering procedures. So I thought it might make it interesting. And then both Lexi and I are interested in data science. And then Lexi mentioned, or I think I mentioned, that Lexi's going to be going into applied math. So this seemed like an appropriate technique. And for the sentiment analysis approach, there's been a lot of studies that use kind of an analysis of language, right? Some of the papers that we talked about how we can kind of analyze these interviews and responses from students to kind of sort them into categories, but there hasn't been much of the natural language processing happening, the actual algorithmic side of things. So we thought that was an interesting thing to do. So that was what we did. Let's take a look at some of our results.
Right, so for this one, these are the 9 problems we gave students and we asked them to group them together. But we kind of want to open the floor to you guys to see how you think that these might be grouped together and what kind of groupings you would expect to see.
So you can unmute if you want or put it in the chat. Either one is fine. We'll give a minute for everybody's fingers to type frantically. One of the things that I naturally thought to look for is just straight up existence versus non-existence. See which of these limits exist, which of these limits don't exist, and maybe just classify them based on that. I thought that might be a popular approach that we could do. Anything else? Well, that was something that I had thought of. Another one is just like function type or things like that, and maybe see what happened.
So
Here's our
these were,
results.
yeah, these were the actual results after we analyzed the student responses. So it's a little different than I think what both of us expected. Can anyone kind of see what the 2 groupings might be?
If there's any themes, one thing to note is that the thickness of the lines connecting each of the numbers represents a kind of frequency. So thicker lines meant that those problems were connected or grouped together more often. Thin lines meant that they weren't grouped together by students very often. And obviously no lines connecting them means that there wasn't really any groupings there.
So this one, it seemed to me chronological, kind of how like the students, when they learned it. So the first side, the left side, the green one, those were some of the first examples that students were taught, and then the right side, the blue one, those examples came later on. So they weren't really classified as existing or non-existing. And function type seems reasonable, but trigonometric functions are not typically first examples. And then the strength between the lines was also interesting, because in the groups, there's a lot, I mean, if you look at the green group, 4 and 1 are really strongly connected, but 4 isn't really connected to the other ones. And then 5 and 1 and 6 and 1 also have weaker connections, and you can see similar things in the blue group.
One of the things that I thought was interesting was that 5 and 6 have a strong connection, and they're both connected to 8 as well. Probably because there's division by 0 happening. And so there's some kind of analysis that we have to do there. So there were likely some students that were grouping things together in the kind of mindset of where are we dividing by 0, which kind of flirts with this non-existence idea. But it's not quite all the way there. There are different types of limits though. And one thing that I noticed is that number 9 also has division by 0 in it. It's just disguised in the cotangent function. And that wasn't grouped with, 5 or 6. It probably was grouped with 8 more because of the trigonometric functions.
Yeah.
So based on how the limit ones were grouped by students, can anyone like think of how they might group the derivatives or any ideas they have for how they might be grouped? I know I was expecting it to be more chronological, kind of like how the limit one was.
So you're saying like kind of your basic limit rules, and then maybe like product and quotient rule and chain rule and things like that, maybe trig functions later on as well. We can look.
Okay, grouping by derivative rule used. That's pretty much how it ended up being. So these were the results for the derivatives. So it was more based on how they were solving these problems. You can also see that this one is a lot more interconnected than the limit one was. So you can see that they have like derivatives not existing. They have the chain rule grouped together, trig functions are grouped together, and then like exponential including ln. So this was different than the limit one with how they decided to group them.
One of the things that we both thought was pretty interesting is that number 3 and number 9 both use product rule. In my mind, those are very similar problems in terms of the actual computation and the rules that you're using, but weren't really grouped together at all. And then the rest of those in that blue group are all chain rule problems, which I thought was pretty interesting. Number 5 and number 4, it's like number 5 is kind of this lone thing only connected with number 4. So probably those are ones where the derivative doesn't exist and students are thinking about that. So there might be some thinking about existence versus non-existence there.
All right, so for the integrals, now seeing how the derivatives and the limits were sorted, does anyone have any ideas on how the integrals were sorted?
I'll wait for some fingers before I click ahead.
I'm so sorry. I'm gonna let my dog in really quick because she's freaking out.
So some of the things that we thought would happen. Yeah, exactly. Kyle is saying sorted by technique, maybe use substitution, your basic antiderivative rules, maybe some like little algebra tricks to simplify things first. You can see a mix of that in here, right? And so there's definitely that kind of a thought. And then the other thinking, well, maybe I won't spoil it actually, because this is one that's going to be the kind of common thing.
Yeah, so the integral one, this was kind of sorted the way before looking at them, looking at the limit and then the derivative, I was assuming that they would kind of be sorted in a similar way. So it's pretty much split up definite versus indefinite. And you can see here the groupings are a lot more, like, they're stronger groupings together. So like 3, 5, 6, and 8 are clearly really strongly together. The lines are thicker. And then the thin line connecting them, that's 8 and 9. We're thinking maybe this is due to them both being polynomials. But then you can see like the 1, 2, 4, 7, and 9 that they all have really strong connections and they're all connected to each other, which wasn't really the solid groupings, and you can really see those which ones they're sorting them in. That wasn't really present in the other in the other surveys.
So this is what we were thinking in summary. When students were thinking about limits, they were thinking about them kind of in terms of like process and procedure, but that seemed to really be chronological in the way that they were learning about these. If you go back to those limit graphs, we can do that later if you'd like. But one of the groups was like kind of very first examples, a polynomial function that was like x squared plus 1 or something like that. That might be an example that I would use as the very first example with limit notation. Another one was a piecewise defined function where we have to think about one-sided limits. Again, these are, really kind of early type examples to build, early ideas of what a limit is. And then our other group was, things with trigonometric functions, which maybe don't get included until after students learn a little bit more about continuity, or maybe something that requires, the squeeze theorem to do, which again is kind of a later technique for students to learn. So it seemed like they was really focusing on when they learned it. And that could have really been kind of a proxy for how comfortable they were with doing those problems, stuff that they had learned earlier, maybe they were more comfortable with. Stuff that they had learned more recently, maybe that they were less comfortable with. It didn't seem like there was any real clear groupings based on whether or not the limit existed. And so not really a ton of thinking about the object like we saw in the literature. It seems like students were really focusing on the procedure of how they might actually, deal with these problems. For derivatives, it was, again, really procedural, seemed to be based on function types. A lot of trigonometric functions were put together, a lot of chain rule composition stuff put together. And so the issues of non-existence, there was really only a couple of derivatives that didn't exist on here, and they did get grouped together. It looked like that was an intentional thing, but that's kind of what we're assuming, or what we're believing, is that that issue of non-existence did get put together. So they might be thinking about these a little bit more as objects instead of just as procedures. And then with the integrals, there was a very clear divide between definite and indefinite integrals, thinking about the nature of these objects themselves. And our hope is that that reflects a conceptual understanding instead of the procedural differences that we use. But also, I think that does go back to that integration paper that we talked about, where viewing these things as two distinct objects is not always a great way of building up themes of accumulation. And so maybe this is indicative of really needing to show off that these things aren't necessarily completely separate, that there is some very obvious link between indefinite and definite integrals. Although I'm happy that the students weren't solely focusing on procedure over the structure of the objects themselves. So what are we doing next, Lexi?
So for the grouping problems, to continue on with that, we're going to look further into the reasoning as to why students identified these certain groups. We did have them put down, explain why they did the certain groups and kind of explain a little more their ideas instead of us just assuming the grouping. So we're going to look a little more into that. And then beyond that, just repeating the study with future classes so we can get more data and see if the trends continue. And then the text analysis that was mentioned earlier. So we're going to be looking at how does student language when talking about limits, derivatives, and integrals change or stay the same on the spectrum of conceptual language and computational language. So to do that, we're going to be building a dictionary in R and then running the sentiment analysis to find these answers.
One of the things that we've talked about in the grouping problems especially is to vary up the kind of diversity, I guess, of the problems that we're pitching them. If you look back at the problems that we gave them, they were all very kind of like parallel to each other, right? Find these limits. And so there really isn't a lot of room for students to balance or juggle the different kinds of mental models that they might be holding, which was fine for our initial pass at this. We really wanted to not bite off too much, but that's something that we're thinking of extending as well. Some other questions that we're thinking of in this kind of ballpark is, this first one is all this stuff that we're looking at, is all of that really just a function of the amount of time that students spend in a calculus classroom? Students learn about limits first, and we probably all have experience, if you've taught Calc 1 before, of students entering a Calc 1 classroom and needing to not only learn the content, but to adjust to that style of a math classroom. It's a different type of topic. It's a different type of exploration and a different type of learning maybe than students are used to. And so there is a transition period where students try and figure it out, let alone the fact that for a lot of these students, this is their first college math class in general. So is all of this really just a function of how comfortable they are in a college math classroom and not so much based on how they're conceptualizing the specific topics? Is it just that as we move out to integration, by that point, students understand the whole idea of calculus a little bit better than they did in week 2 when they were talking about integrals? So that's something that I'm not sure how we will explore that fully. Maybe it just means we kind of do this type of thing with students that aren't necessarily enrolled in Calc 1 currently, but have maybe completed the course. So we'll have to look at how we might tackle that. Other questions that we might want to be asking is, what are the models of limits that we present to students compared to what they're perceiving? I really wanted to at first do this survey twice and do it with students and a group of faculty that teach calculus at the same time, and try and get like, not an answer key, but at least some sort of a baseline thing that we could compare to. I have my ideas of how I might group those topics and how I might talk about things, but it would be interesting to see how that holds across a whole group of faculty teaching these kinds of courses, especially when we look at the literature and we found, like Lexi was talking about, there's some pretty clear evidence that students learn this stuff differently than the way that we present them. I think it would be really helpful to see where those differences really show up, and to see if we can investigate why that is. And then lastly, how much influence do some of the big results from a standard calculus course have over how students perceive these? I know in my courses, the fundamental theorem of calculus is like the pinnacle. It is the biggest of big results that we talk about all semester, and that's the thing that ties together all of those themes. Like we mentioned in that paper above, that comes really late in the semester. So what I'm curious about is, what are the other big results that show up that really form in students how to think about these topics that maybe I'm not aware of? I know the fundamental theorem of calculus is a huge one, but in week 5, in week 10 of a 16-week semester, what are the results that are really formative? That way we can focus on how we're presenting those to make sure that we're not only building, intuition, but also good and helpful intuition, and, connecting those things thematically as well. Here are those resources. Here are the links to the papers that we had, although the links are also in the chat. I know that's not the full hour. We were expecting to not quite go, 45 minutes or anything like that, just to have room for some questions afterwards, and then let you all get on with your day as well, and start this weekend out. But if you have some questions, we would love to stick around and answer those and chat more about all this. So let me know if you have any questions, but thanks for listening to us and showing up to our talk.
Do you guys have a significant number of students who've already had calculus experience when they start Calculus 1? And do you think that skews these results in some way?
Yeah, Jim, that's a really good question. I think we do, and my personal opinion, or my intuition, is that that's really dependent on the semester. I think our fall semester, I think we get more Calc 1 students that have some calculus background, and part of it is some of the really cool programs that we have. One of the things that I keep pointing to at my institution at Moraine Valley is that we have this transfer articulation with engineering students to some of the different four-year colleges in the area. And one of the requirements of that program is that those students that are going to go through with that and get the automatic, enrollment in these other engineering programs after year 2 is that they take Calc 1, whether they have AP credit or not. So I've noticed that my fall semester Calc 1 classes are filled with students who have a ton of calculus experience, because those, engineering pathway groups come in needing it, whether they've seen it or not. And I think my spring semester, I have fewer students who have calculus background. So I would be really interested to see how this might differ by semester.
Yes, it might. The other thing is, in second semester, if you have these students with calculus experience, it's often a very bad experience they've experienced. And, that it's more likely that they've had a positive experience if you see them in the fall, but not always, not always. That was the thing that I think is very difficult as an instructor to really, when I've had too many students where the bloom is off the rose. They want to use L'Hopital's rule on some of the most basic things that involve rational functions. These are absolute, in many cases, they'll misapply it, which is great, because then I can, back them up a little bit and say, no, just a second here, when does that apply? But there are, there are too many cases where I am not the first person to be explaining these concepts in their direction.
Yeah,
and in too many cases, a lot of what I would want to say was not what was said to them, or at least not what they got.
They're retaining, right?
Who knows?
Exactly.
Who knows?
And I think that that's was kind of mentioned in that in one of those papers that we talked about too, is that so much of how students view it was specifically through the lens of limits, but I think this would be true for all of the calculus topics. So much of how students view that is formed, before they enter our classrooms. Which is difficult. I think it would be really interesting to try and investigate how to construct or build a classroom in a way that kind of pulls down all of those preconceived ideas and builds, an intuition from foundation up. Personally, I think that would probably take more than a semester.